Et la même chose, vous êtes bienvenue, nous sommes en live.
C'est en live?
C'est en live, c'est notre Samir. C'est le professeur Abou Souror qui sera le chair de cette session, qui sera dédié à notre frère et collègue, M. Samir Adly, excusez, parfois je suis fatigué là, c'est le grand professeur que je connais de la France. Ah oui, particulièrement. Je le sais un petit peu, qu'il parle un petit peu de son...
Bon, c'était un grand professeur. On vous avait dit tout. C'est un grand professeur de international. C'est un sujet intéressant.
Merci. Merci. Chaud, là,
oui, avec plaisir. On va commencer à 17h. Et c'est quoi le chat?
Alors, notre grand professeur Samir Adly de l'Université de Limoge va nous présenter un sujet, vous allez voir, il est très intéressant. Donc, sur le thème Navigation to the World of Non-Small Dynamical Systems.
Merci. Merci. Bon, j'imagine que je dois parler en anglais, mais avant, je dois dire quelques mots en français pour remercier d'abord les organisateurs, en particulier mon ami Abdelatif Lahafia, qui s'est donné à fond et elle a laissé toute son énergie. Et je pense que ce soir, tu dormiras très bien. Et c'est vraiment un grand plaisir et un grand honneur d'être là. Donc j'ai fait plusieurs conférences, mais il y a des conférences internationales d'envergure avec 2000 participants, avec des frais d'inscription très chers. Et il y a des conférences de taille humaine et moyenne et qui sont très amicales et on apprend beaucoup de choses. Et donc c'est lopal', qui est une série qui va démarrer, que j'espère va continuer, est un exemple parce qu'on voit bien comment on est traité ici. Donc un grand merci à Adly pour toute l'organisation parfaite jusqu'à maintenant que tu as pu mettre. Voilà, il y a un grand merci à tous les étudiants et collègues qui sont courageux de rester jusqu'à la dernière minute. Donc je ne serai pas là. Voilà.
Et il a fait ça exprès pour nous à la fin, pour que tout le monde va assister.
So now I will switch to English because there are some colleagues coming from other countries, non-French-speaking countries. And as you see, the topic of my talk is about a personal invitation to the world. And this world, I call it non-small dynamical systems. And I have to explain exactly what I mean by non-smoothness. Okay? And the first example that I want to mention is that we can explain really maybe very hard things even to children if we put a lot of pedagogy. Okay, it's important. For example, when I was preparing this talk, so one question happened: what does it mean if you have a person who is not a mathematician, even not a mathematician on computer science? we never heard about non-smoothness. What do you mean by non-smooth dynamical system? You can explain it in a very really good thing. And the good example is the bouncing ball. I want to show you exactly what I mean by the bouncing ball. If you don't know this software, maybe I have to switch to the mic. Is that okay? Okay. So this is the GeoGebra, and I want to simulate a very simple example, which everybody knows here, this bouncing ball. Like for example, the basketball or the tennis ball, right? And you take this. If I have to put here, I change the coefficient, restitution, I put 0.9, okay? And here you have the radius of the ball. If you don't know this, GeoGebra is very nice software. As you see here, you can take, this is the radius of the ball. Here, this is the coefficient of restitution. The restitution is the energy that you communicate to the system. If this is around 1, it means that is exactly, let's take it 1, you will see this is a periodic motion. It's only a periodic motion, as you see here. There are no friction, okay? And the bouncing is periodic all the time, okay? If you put this coefficient around, let's say 0.8, it's small. As you see, the ball will bounce, but it will dare, and sometimes, well, at the end, it will stabilize to 0. Right? And if you put this coefficient, let's say around very small, 0.5, as you see, this is what we call the inelastic shock. Okay? It means that the ball will stabilize immediately. It depends on the material. This is what we call the coefficient of restitution of the energy. Okay? And here we can change the gravity if you are, for example, in Earth or Moon, etc. You can change the gravity. This is the first example that I want to mention in my talk concerning non-smoothness. And in this particular example, the non-smoothness comes exactly from the fact that when the ball hits the floor, the velocity is discontinuous. What does it mean? You have right velocity and left velocity. It's like the BR, when we are playing for the BR, you hit the ball will hit the boundary. And you have two velocities, the right velocity and the left velocity. So it means that as a function, the velocity is discontinuous. Okay? Because for students, when you see that the function is discontinuous, if you have, for example, the right limit is not exactly the left limit, right? So now, what happens if this function is discontinuous? I want to differentiate this guy, because if you want to apply the Newton's law, Newton's law says that the mass times the acceleration is equal to the sum of the forces, right? So what does it mean, the acceleration in this case? If the velocity is discontinuous, how can I define the derivative of the velocity, which is exactly the acceleration? So now we have a non-smooth problem. So mathematically, you have to set exactly the functional framework, what we call the functional framework, in order to deal with the acceleration. I will return back to this matter later to define exactly the framework. This is the first example that you have to understand that non-smoothness of non-smooth dynamical systems is the bouncing. And the second example is the Coulomb friction. You know, when you are walking on the street, etc., without Coulomb friction, this is what we call the dry friction. You have the viscous friction and the dry friction. And the dry friction is a very complicated phenomenon. It's a very complicated nonlinear phenomenon. Let's say that the right model that we are using right now comes from Charles Augustin Coulomb, a French physicist, okay? And he was born in Angoulême, and as you see, Angoulême, Limoges is not far from Angoulême. It's 100 kilometers from here. as you see here, and we are not far from Bordeaux, okay? He was born in Angoulême, and he died in Paris, he was in the Academy of Science, of course, and he graduated from the École Royale de Génie de Mézières, and he put this model that we call the Coulomb model for dry friction. I want to explain to you this exactly. This is a simplification of the real Coulomb model, and the forces we have, for example, here, a very simple 1 degree of freedom. You have a mass of stiff, this is the spring with the coefficient, the stiffness coefficient, which is K, and here we have a damper. This is the coefficient, damping coefficient, this is viscous friction. But the mass is sliding on the floor. It means that when you have contact of the floor with the mass, there is friction. And this is dry friction. And the model of this dry friction is important. Because if we are walking, if we are driving a car, etc., the contact with the tire, with the floor, everything is connected somehow to this dry friction. And Coulomb 300 years ago put this model that we still use right now. Okay, what says exactly that the forces? Okay, you have a force, you have to measure the force here. There are, if the velocity, it is, how to say, proportionate to the velocity, but not exactly to the velocity, but to the sign of the velocity. If the velocity is not 0, then F will be exactly, this is what we call the dynamic coefficient, okay, times the normal load, okay, of the forces. This is the normal load, F, normal component of the forces, F times the sign, and the sign will be -1 or +1, right? But what happens if the velocity is 0? So if the velocity is 0, you have to take all values between minus this static coefficient that I call μs and the normal load, times the normal load. And this is the interval. Let's say minus this coefficient plus this coefficient. This is the whole interval. And as you see, this problem is not smooth. Why it is not smooth? Because we have a discontinuity to go from minus this coefficient to the plus this coefficient. Okay? And this is the Coulomb friction is a good example for non-smooth dynamical system. And if we want to take into account this, what we call in mechanics the stick-slip conditions, you have maybe this coefficient mu that I have here could depend on time, sometimes it could depend on the velocity, and sometimes it could depend on both. Time, velocity, and acceleration, and position. Time, position, and velocity, right? This is, for example, in earthquake, in order to simulate maybe taking the coefficient dependent on this parameter and to adjusting this coefficient is a very challenging problem, okay? So now, if you write down this dynamic, you have the mass times the acceleration times this is the viscous friction. And I want to explain the difference between the viscous friction and the dry friction comes from this. Here you have a sign of the x term. This is a nonlinearity. Okay? Well, if you don't have this sign, it's exactly c times the velocity. It's a linear function in the velocity. It's only linear function. So this is smooth. So you have here the mass times the acceleration. This is the viscous friction. And you have here, this is the stiffness of the potential, if you want. But here, you have, since you have the whole interval, you will have an inclusion. It's not an equation, it's an inclusion. So this is the dry friction, the Coulomb dry friction, since I put this as a coefficient gamma, and you will have that the velocity, when the velocity vanishes, you will have that, the value at 0 will be the whole interval. This is why if you want to set for simulation the phase portrait. Okay? The phase portrait of this model is exactly what you have here. This is the static, this is a steady state equilibrium point, which is the whole interval, and all trajectories will be attracted by one of these points. We don't know exactly which point, because we have a lot of equilibrium points, okay? Not isolated equilibrium point, not one, but the whole interval, okay, is an equilibrium point, right? And all trajectories will be attracted by it. This is a good example of no smoothness. But before talking about no smoothness, we have to return back in the past and talk about nonlinearity. You know that in mathematics and physics, we talk about linear model, and after that, just after that, we have nonlinear model. And the nonlinearity, we can find it, for example, if you are working on switching systems, power converters, electronics, for example, DC-DC, buck converters, diodes, etc. I will talk about this. Or we can find another series of examples coming from complementarity system, evolution variational inequalities, differential variational inequalities. I will explain that later. And also sweeping processes, okay? And the Filipov systems, okay, will constitute a very good topic for nonlinear system and non-smooth system. And differential inclusion, including the dry friction. But the bouncing ball, for example, belongs to this class of problems, which I call measure differential inclusion. I will explain this just later. Why measure differential DVI, measure differential inclusions, means that the state will jump and we have a discontinuity in the state. We have impact or vibro-impacting systems. This is vibro-impacting machines, for example. If you are working very hard, you can walk deep in the ground, something like that. This is their impact, and every time you have impact, you have no smoothness. And you have a measure, because you have to give a sense to the acceleration. Okay. So, non-smooth, what does it mean? What we mean by a non-smooth system, in your opinion? Everybody knows what we, in mathematics, for example, we call a smooth function. What does it mean? A function is smooth, maybe differentiable of class C1, class C2, class C infinity, okay? It depends. But it's a vague terminology to say, okay, non-smooth systems is a system which is not smooth, okay? So it means that we lose some properties of linked to the differentiability of the data. This is important, okay? But the data here is what exactly? Since talking about dynamics, the data here is vector field, because you have a dynamic. X dot equal to something, okay? Look at this example. This is another example when we have nonlinearity. This is what we call the buck converter. What does it mean, the buck converter? The buck converter is a very simple device, but we have it everywhere, in the smartphone, in the laptops, in computers, etc. It converts, it consists first, this is a load, this is the loads, let's say, for example, 9 volts. We can take here 9 volts. We have a diode. I will suppose that my diode is ideal. I will explain to you what I mean by ideal diode. I have here a capacitor, and I have an inductor, L, and I have here a resistor. And here we have a switch which open and close. Okay? So this kind of system, we call this buck converter, because it converts, this is DC-DC, it converts from high voltage to lower voltage. Let's say, for example, you need from 9 volts, you need only to have the output equal to 3 volts. This could happen. And you have it in your laptop, because if you give 9 volts, for example, in your smartphone, the processor will die. Okay? This is important. And you have this buck converter everywhere. You have to convert from high to low level. Okay? And the opposite exists also. What we call this, the opposite, we have small voltage and we want to convert it to high voltage. This is what we call the boost converter. The boost converter. So, the nonlinearity here comes from exactly because this is a constant voltage line. This is the input. This is the diode, this is the capacitor. The capacitor is a smooth element because the link between the current and the voltage is very smooth. The inductor is very smooth, and the resistor is smooth because it's linear. If you suppose that it's linear, you know that V is equal to R times I, so something which is linear. So everything is linear. So the non-smoothness comes from what exactly? It comes from the diode. Okay? So, the diode, why the diode? You have here, if you suppose that your model, this is the diode, which is a rectifier that allows the current to flow in one direction and restrain it in the opposite direction. It's like a switch, okay? And we can model this ideal diode because as you know, in physics, every electrical devices, we can characterize it by what we call the ampere volt characteristic. What does it mean, ampere volt? Ampere, this is the current, I. Volt, this is the voltage. You measure the voltage, the current and the voltage. Okay? And you have this characteristic for the ideal diode. What does it mean? So when you are here, the current flow, okay, the diode is conducting. But when you are here, the diode is blocking. This is what we call in our language complementarity system. This is a complementarity relation. Why complementarity? Because you have that minus VD, which is here, it's non-negative. I is non-negative, and there is orthogonality here. It means that each time one of the component is zero. Okay? This is what we call a complementarity. And one question, I will return back to this later. One question that could happen is, could we find a function, a scalar function, that when we derive it, we get this graph? It means that we are talking about the potential theory. Okay? The potential theory, what does it mean? That you know that the electrical potential comes from E is equal to minus gradient of V. V is the potential. So could we? The function is very easy to find since it is the indicator of R plus. It means that this is 0 and plus infinity here everywhere. Okay? So if you derive this function in some generalized sense, we'll take it here in the convex subdifferential case, okay? We'll talk about the subdifferential later, but anyway, if you derive this function, you get this graph. So we'll go from here to here by derivation, and then from here by here by integration. So there is a link, and the link is the potential, okay? So now, if we remove, just because we can keep this for the boost or the back converter, if we remove the diode, we can build this circuit very easily, okay? This is the circuit that we can build, okay? This is the inductor, the capacitor, and we have here the resistor. We remove the diode. We can keep the voltage, for example, to 3, it's possible. But what happens if you remove the diode? Your circuit will burn. So it's not stable, okay? This is a problem. So now we cannot avoid this non-smoothness. It's not possible to, okay? So now, as I told you, non-smoothness is linked somehow to the vector field or to the trajectory if you are talking about dynamics. So here you have, if you have an ordinary differential equation, this is the vector field, this is the initial data, and x of t is the trajectory. If f is not very smooth, it means C1, C2, maybe Lipschitz, etc. It will influence the behavior of the solution. Okay? So, I think that students who attend differential calculus can understand that if we have classical existence and uniqueness for this ODE, ordinary differential equation, if, for example, the vector field is Lipschitz continuous. It's enough to get existence for each initial data. If I give you the initial condition, you will get an unique trajectory. But as I told you, there are some situations when f, this vector field, is not continuous. This is the case, for example, the dry friction, because you go from minus gamma to plus gamma. This is discontinuous. So the vector field is discontinuous. So how to give a sense to this dynamic? Okay? How to give a sense to this dynamic? So, one of the famous books written by this Russian mathematician Filipov, and everything is in the title. You can download it. Look at the title: differential equation with discontinuous right-hand side. It's exactly fit in the dynamic of no smooth. Okay. So in this book, so Filipov handled discontinuous vector field, okay, by setting these two differential inclusions. Okay, I will return that to this example. And another example that we can find is sometimes we have some systems which are smooth in a part and not smooth in another part. They smooth in two parts, sorry, but when you cross the boundary between the two parts, no smoothness happens. This is the example. You have two regions, okay, and you have a switching, what we call the switching surface, sigma, between two regions. If you are in the region 1, this is a simple ordinary differential equation. If you are in the region 2, exactly ordinary differential equation. But when you cross from this region to this region, you have to go through this switching surface. If you go there, no smoothness appears. Okay? So no smoothness appears here. This is, and one example which is, there is a problem of connection, Zakaria. It's not smooth, exactly. Zakaria is not. I think that I lost the connection. I'm just okay. In error.
I'm correcting my ears.
47. I lost the connection. Okay. So now, I'm sorry about that. This is, I will return back to the bouncing ball because it's a very nice example. Okay, that even a student can understand. If you write down, as I told you, for the bouncing ball, if you write down the Lagrange equation, this is the mass times the acceleration, which is equal to the sum of the forces. You have the weight, have some control, and here you have a multiplier that we call the Lagrange multiplier, lambda. And this lambda, because the position is positive, lambda is also positive, and you have the complementarity. Okay? When you have contact, okay? When you don't have contact, lambda is x is strictly positive. We don't have contact because the ball is in the air. You don't have contact. X is strictly positive, which means that lambda is 0. We will not activate any Lagrange multiplier until we have contact. When we have contact, it means that x is 0 and lambda will be strictly positive. This is, we will activate the Lagrange multiplier only when we have contact. This is the explanation of this complementarity relation. Okay? And the second, what does it mean here, this relation? This is the right velocity and this is the left velocity. And the right velocity is minus some coefficient, E. If you remember, I call this coefficient the restitution coefficient. It's always between 0 and 1. 1 is It means that you restitute the whole energy. 0 is the inelastic shock. Okay? And you see here, it depends, this is what we call the impact torque. But since the velocity is discontinuous, you have the left and the right are completely different, you have to give a sense to the acceleration. So in your opinion, the acceleration will be what exactly? Will be, because if you derive a function which is discontinuous, you could have a Dirac measure. Okay, you could have a measure. This is why we call this measure differential inclusion. Okay, so the acceleration is a measure. Okay, so lambda is also a measure. Okay, and if x is strictly positive, it means that we have only a classical smooth system. The ball, when the ball is in the air, everything is smooth and it's a very simple dynamic. And when we have contact with the floor, here we have no smoothness. The velocity jumps, so we have to write down this in the framework, also what we call in mathematics the bounded variation tension. Okay, BV tension. And if you look at the simulation, you have here the bouncing ball, as I showed you in the beginning of my talk, if you remember. And if you look at the derivative of this position, you will see that the velocity will switch from this to this. So the left and the right are different. Okay? And this part, the velocity is smooth, it's linear, and you smooth from this part to this part is not smooth, etc. At each impact, the velocity will be non-differentiable. So it means that if you want to derive this, you will get some Dirac measures. Okay? Still Dirac that you get here. So this is a good example. It means that no smoothness is a part of our work, and the only thing that I can say is that before our mathematical tools cannot handle this kind of mathematics. But now we have a lot of tools coming from function which are not differentiable. Function we can talk about sub-differentiable functions, etc. by using non-smooth and variational analysis. This is the topic in mathematics that we call non-smooth and variational analysis. It's completely different from the classical analysis. The classical analysis that you learn at school is completely different. Okay? We don't need differentiability, okay, of the functions. So now, another example is this mass hitting this wall. As you see before the impact, everything is smooth. And after the impact, you have no smoothness, which occurs here. And the dynamic is very easy to write. Okay? It's the same. Okay? And you can write it like this, as we have here a normal cone. I will not go to such details, but here we have a normal cone to this set k. K is only the minus infinity n, right? Anyway, could you please, someone know exactly what this exactly? Who knows what is this? Could you guess what is it? Yeah? Okay, maybe it's not. I will give you a hint. You know this? This is what we call a circuit breaker, disjunctor, of course. You have this at home. Everybody has it. You cannot avoid this. And if you enter into the detail of this mechanical, it's a combination. It's a combination of mechanics and electronics. This is why we call this mechatronics. Okay, combination of mechanics and electronics, and you have here a lot of beautiful mathematical problems. Okay, you have impact, because each time you have something wrong with this disjunctor or this circuit breaker must stop the electricity, and to design such the companies are like, for example, Legrand, which is in our city in Limoge, and you have Schneider. You have a lot of companies. I have some colleagues working just to design such a circuit. It costs a lot for the company to design the circuit, and in order to design this, you have to understand the mathematics behind it. As I told you, there is a combination of impacts, because here you have the impact. Every time you have the circuit must stop. Tack. You have impact problems, which means no smoothness. And in order to simulate this, you have to write down the equation. And you have to deal with no smooth problems. You cannot avoid it. Okay? So, in order to understand the general framework that we are talking about today, we have to talk a little bit more abstractly. Okay? What we call a mechanical system is mathematically only is a triplet that you have here, U, F, two subspaces, and a scalar product between the two spaces. U is the space of velocities, okay? The velocities was also the displacement. I will call the element by small u, this is capital U, and F is the spaces of forces, and all forces will lie in this big space, this vectorial space, we call it F. Okay? And the U scalar F, this is a scalar product that you have, and the mechanical meaning of this is the work of the force F for displacement U. Okay? The work of the force F, for each force F, you have a displacement, and the work, this is a scalar. Okay? Scalar. And if you consider a multi-valued mapping A from U to F, okay, which transform every U to a force, every displacement to a force. Okay, let's say F, if you give me a displacement U, I apply this operator, AU, I will get forces. I give you some examples so you will understand very well. So we return back to the potential theory. We say that the forces derives from the potential if we can find a function which is of class C1, okay, such that F is minus the gradient of P at U. Everybody knows exactly what is the definition of the potential. Okay. It means that we say that the forces derive. The best example maybe in electricity that you have that the electrical E derives from is equal to minus the gradient of V. V is the potential, right? And I give you here another example. If you take the resistor and you are looking for the IV, the current versus the voltage of this I, you will see that I, V is equal to Ri, which is, we have this linear relation. This is the graph of the IV, okay, of the resistor. And if I take this, my question to you, do you think that this graph derives from a potential? It means, can I find a function such that when I derive this function, I get this graph? And the answer is easy because this is linear. If you derive a parabola, you will get this. So this is what we call the power function, which is the potential. If you go from this graph to this graph by derivation, okay, and you go this graph to this graph by integration. This is the potential theory. And the function here is smooth because it's a parabola. This is smooth function. So the resistor, this is why I told you from the beginning the resistor is a smooth element. It's a smooth element because you have here nabla, which is the gradient, and the function is C. So now I want to explain to you how to generalize this to non-smooth functions, to the functions which are not differentiable. And the first person who introduced this is Jean-Jacques Moreau from the University of Montpellier in France. Unfortunately, he died in 2014. Okay? He was both mathematician and mechanician, and he got this fantastic idea that it is possible to generalize the notion of the potential by using even for functions which are not differentiable, but convex, let's say for convex functions. And he published this paper. This is a crasse, a compte rendu de l'Académie des sciences de Paris in 61. Okay? And la notion de surpotentiel et les liaisons unilatérales en élastostatique. It's in French. Okay? He introduced it. And what says exactly? It says exactly that if you take a diode, okay, this is the IV characteristic of diode that I already explained, okay? And if you take this function and you differentiate it in the sense of convex analysis, you will get this graph. Exactly. This is the superpotential of Moreau, Jean-Jacques Moreau, okay? And the link between now is very well known because when this mechanical law is only a singleton, which means that we have only one element inside, we get the potential theory. If our functions are convex, we get, if our function is convex, lower semi-continuous and proper, okay, we get the superpotential by Jean-Jacques Moreau. But in mechanics, sometimes we don't have always the convexity, because the convexity, if you, in terms of the derivative, it means monotonicity of the operator. Everybody knows that a function f is convex, is on if and only if the gradient is monotone. Okay? So here, for example, we can have the relation between the string and the stress, okay, the displacement, could be non-monotone. It's not monotone. You see here that this graph is not monotone. And this graph also is not monotone. So, a modern mechanician whose name is Palagiotopoulos, in 1981, he introduced the non-convex superpotential by using another subdifferential, which is not the convex subdifferential, but we call this the Clark subdifferential. Okay? For local Lipschitz, only for local Lipschitz function. It means that he relaxed the condition from convexity to local Lipschitz by using another type of subdifferential. Sorry. Okay, so now the link is clear thanks to Jean-Jacques Moreau between variational inequalities, complementarity problems, etc. Because you can find here, as you see here, this is a variational inequality formulation of first kind, second kind, and here you have complementarity. Okay. But I will not go to such detail. So now I want to turn back to electronics. So, if you remember, I have just to look at the IV characteristic of any electrical device and to see if it is smooth, non-smooth, monotone, not monotone. Okay? We will do a small exercise. So take any catalog of any company that you have on the net, for example, just Google it and try to find this the IV or the ampere volt characteristics of these devices. You have the diode, the Zener diode, the varactor, the triode, the tetrode, the transistor, the diac, the triac, the silicon control rectifier, which is here. All these components, we use them every day, okay? In our smartphones, in laptops, etc. Okay, let's go, for example, to the first model, what we call the diode model. This is the very simple model because it's a simplification of the ideal model. Because V1 is very small, because V1 is almost zero, okay? But minus V2 is very big. So it means that it's a truncator of the ideal diode, because the ideal diode, you have this here, this graph. In your opinion, this model is smooth or non-smooth? It is not smooth because you have jump. You jump here. Is it monotone or non-monotone? It is monotone because you go monotones in R2. It means that if you are the curve must be increasing. If you cannot return back, okay? If you are drawing something, you have to keep going, okay? If you go here, look at this, it is a monotone. So it derives from Moreau's subdifferential, okay? It means that this model comes from the Moreau's potential. You can find the convex function. When you derive it, you get it. And if you remember, this is exactly an analogy between mechanics and electronics. This is exactly the dry friction of Coulomb, if you remember. Minus gamma and gamma, if you remember. It's constant, minus gamma, gamma, and gamma. Okay? If you look at this, it's an analogy between electronics and mechanics. Okay. Look at this graph. This graph is monotone. It is monotone. So it derives from Moreau's potential. Okay. So this is what we call the complete diode model. Did you hear about Zener diode? You know, Zener diode. The Zener diode. If you look at the Zener diode, is a good voltage regulator to maintain a constant voltage regardless of some minor variations in load current or input voltage. Okay, small variation, you must stabilize your system. And if you look at the Zener, the IV characteristic of the Zener diode, you will get this graph. And this graph is monotone, so it derives from Moreau's potential. Okay? So I will give you some examples which are not monotone. Let's take this one. This one is, we call this the diode alternating current, the D diode alternating current. And we have the characteristic which is like this. Look. And this is not monotone. So it derives, we can find the local ellipsis function. When you derive it, you get this graph. And usually, because since we have here this part which is set value, usually engineers get a small approximation because it's set value, it's vertical branches, you put it to a small branch like this. This is the approximation of this. Okay? And another example, and I think that I lost the connection. It's a problem with the. I'm sorry about that. Yeah. Okay. Okay. Yeah. This is another electrical devices that we have when we have the characteristic. As you see, this is what we call the silicon controlled rectifier. Okay? And the silicon controlled rectifier, you see the characteristic is like this. It's not monotone also. So it derives from Panagiotopoulos, let's say, potential. You can find the local ellipsis function. When you derive it, you get this. Okay. So I'll give you a simple example to show you that convex analysis can help engineers, okay, to get simulation very easily. This is well known in electronics. What we call this is the clipping circuit. The clipping circuit is very easy to, you have here an input, U of T, and you have here a resistor, or diode. I will suppose that my diode is ideal, and here we have a voltage, supply voltage, let's say, for example, E equal to some constant, 9 volts, 3 volts, whatever, okay? And the idea is to write down the equations, okay? And since my diode is ideal, thus the system will be non-smooth, of course. I will use tools from non-smooth. I write down here just as you see here, this is the Kirchhoff laws in electricity. If you now remember, the voltage KVL, Kirchhoff laws, and you have the current Kirchhoff. This is the voltage, and you get this equation. It means that you use that the fact that the identity that the normal cone inverse is only the projection over R plus, and the projection operator over R plus is the maximum between 0 and U. And you will get easily that when U is less than E, the diode is broken, and when U is greater than this supply voltage E, the diode is conducting. So to get a simulation, imagine that you have a wave form, a sinusoidal wave form, U of t, this is the input. What would be the output? The output can be easily computed as this. Since I took E is 1, so the output will be the minimum between U and E. Okay? Minimum between U and E. And C, this is the input, this is the output. Very easy to understand because the minimum between the two. So now I can put more complicated systems. For example, I have 2 diodes here and 2 supply voltage. You write down in the same way the Kirchhoff voltage laws, okay? And look at the simulation. This is the input, the output, because E1 is 0.1, you cut at 0.1, and E2 is 0.6. You cut at this. This is the output. So it's very easy. It's 2 lines proofs for students who don't know. For example, you only have to know that the identity plus the normal cone inverse is exactly the projection. Okay. So now, if I change the diode, because I put the diodes here, ideal. If, for example, I change the 2 diodes, I put a diode, which is not monotone. I will get, this is the input, which is a wave form, like this. Look at the output. Okay? Another complicated circuit. I change here, I put here a silicon control rectifier, okay, where the characteristic is this, non-monotone. I put here a Zener diode, which is monotone. Okay. What will be the output? Look at the output. I have the same problem. This is the output. Okay? This is the output. A more complicated circuit, because maybe you can say that, okay, there are only some simple circuits, but here another complicated, this is what we call the sampling gate. And the sampling gate circuit is a circuit in which the output is only on a production of the input waveform during a selected time interval. Okay? And you put 0 outside this interval. So now, if you put down the equations, you have this is the output, the input, as you see, the output. It means that in this interval, it's exactly the same, but here you put it to 0 in this interval. Okay, it's the same, and here's 0. This is the sampling gate. The sampling gate. Okay. Okay. So non-smoothness, we have 2 kinds of non-smoothness. In optimization, we know that non-smoothness in variable spaces, okay, in variable spaces, because in general, when you deal with constraints in a feasible region, and in general, you want to minimize the function, the minimum is in the boundary. Okay, so we have to give a sense to the normal cone to this one. This is what we call the non-smoothness in space. And you have no smoothness in time interval. This is the boundary law, for example. In this example. Okay. I will skip this part, and I want to just to show you the other topic about the sweeping process. That I have. How much time do I have? Okay, this is good to finish with this. So context. This is the sweeping process introduced by Jean-Jacques Moreau And I will explain the dynamic. Look at this dynamic. U dot is minus normal cone C of t at U. And in order to give you a general idea about this, Jean-Jacques Moreau wrote more than 25 papers about this sweeping process, problème de Raff de Moreau in French. And the first paper is here. And he modeled this from problems coming from mechanics, okay? Anyway, you have a set which is moving in time, C of t. This is my set. At initial time, you have this shape. Another time, it could change the shape, okay? It moves with respect to time. And the best example, if you have a polyhedral set, when the constants depend on mountain time, okay? And look at, for example, this set moving. And if you write down the equation, look at this. If you have this set and the ball. If the ball is inside the set, then the normal cone is reduced to 0 if you are in the interior. And in this case, nothing happened. So the set will move until the boundary will touch the material point, and it will push the point inside. Because this is why you have minus here. Okay? So you have the normal cone, the velocity will be inward because you have minus. Okay? Anyway, you have. I want just to finish this talk. This is the catching up, and this kind of problems we can find them in many applications. Let's say, for example, in granular material, planning procedural economy, you have electrical circuit and mechanical system, and more recently in crowd motion. For example, I want to give you this example, and to finish with this. Okay. For the crowd motion, this is the situation where we want to evacuate. Emergency evacuation of people in this room, for example, and to avoid congestion in the world. Okay, so if you have a lot of people, okay, the pedestrians in the street, for example, or in a building, you have many floors, and you want to avoid these obstacles, and you have only one exit, and you can model because Bertrand Maury and Juliette Venel, they use this sweeping process, Moreau sweeping process, to model the crowd motion, okay? The evacuation, emergency evacuation. I want to run this video for you in order to show you exactly. So for students who want to learn more, this video that I run is not mine, it's done by Juliette Venel that I took from her website. And for students who want to learn more about it doesn't work. I don't know. Just okay. So students who want to learn more about numerical simulation, there is a software called Psychonos, okay, for no smooth numerical system. You can, with this software, you can download it. It's into the net, mechanical systems, you have switch electrical systems, you have sliding modes, biology also, and many problems. And students who want to learn more about mathematical backgrounds, coming from mathematical background about no-smooth systems, can read this book about variational approach to no-smooth dynamics with many applications in the natural mechanics and electronics. And some references here, okay, that you can find that I used for this talk, so you can find. So I give you just a small snapshot about no smoothness, and I hope that you just keep in mind that no smoothness is everywhere in our daily life. The only problem that we don't maybe have the mathematical tools to handle these problems. So thank you very much for your attention. I'm sorry for the inconvenience concerning the video projector.
Merci Samir de l'excellent sujet. Si vous avez des questions.
Il n'y a pas de questions.
It's possible. Yeah. You are, there is, of course, you have to avoid the obstacles, but you can add obstacles in order to avoid them. But this is only the numerical simulation that I say, that we cannot predict this before. So you are talking about crowd motion, right? Yes, okay.
Vous donnez des questions en France.
En français, c'est des questions en français pour les étudiants qui veulent poser des questions en français. Une question, une étudiante. C'est une bonne chose que les étudiants posent des questions.
Je veux savoir quelle est la différence entre function response ou différentiel, fonction non différentielle.
D'accord. Ce que j'ai dit tout à l'heure, c'était ce qu'on appelle en français on dit non lisse ou non régulier. C'est un mot générique qui cache beaucoup de choses. D'accord? Et ce que j'avais dit, une fonction dite non lisse, elle n'est pas lisse. Donc, mais qu'est-ce que ça veut dire une fonction lisse? On dit qu'une fonction lisse, pour M. Armstrong, peut-être c'est une fonction qui est C1. Mais M. Lafay, il est très trop exigeant, il va demander C infini. Je le connais, c'est l'éducation de Donc, c'est différent, ça dépendra de chacun comme moi. Mais moi, j'utilise un terme générique, vague, qui dit lisse, mais qui cache beaucoup de choses. Mais au moins, qu'elle soit différenciable. D'accord? Au moins, minimum. Mais ça peut être C2, cette fois, C infini. Okay? Chacun de... Donc, c'est pour ça que non lisse, c'est un mot non smooth, générique, qui cache beaucoup de choses. On met dedans un tas de... Ça va des fonctions qui sont... il y a des fonctions continues, mais qui ne sont pas lisses. Il y a des fonctions qui sont discontinues, comme par exemple le frottement sec, mais ça cache beaucoup de choses. C'est un mot générique. Je suis d'accord que c'est pas très précis. Hein. On ne peut pas le préciser d'accord. Il y a d'autres questions? But it depends what you want to do with the data. You have data, for me, if you have data, image processing, you have, for example, of course, because there is optimization behind. If you have data, you want to minimize something, and of course, if the data moves with time, you have a dynamic. You can, if you write down the dynamic, it's in the framework of this exactly that I call non-smooth dynamics. It's no problem. No problem, we can handle this. But what kind of, this is a good question, what kind of mathematical question that we can ask? This is, I did not have time to explain this. There are only, we are interested in what we call the well-posedness. It means that to show that the problem has a unique solution, or has no solution, okay? Or the stability analysis means that if you perturb slightly the data, the problem must have also a solution. The problem is stable in the sense that the dynamic must differ. And the control analysis, when we don't have stability, can we inject a control to get this problem stable? And after that, we can have numerical analysis. It means that you have to study numerical algorithms to simulate your problem. This is the kind of the question that we are interested in. But it's a general problem, could be applied to many branches of science, but it's a problem that we have. Thank you. Merci d'être resté jusqu'à la fin. C'est difficile.
Oh non, c'était pas difficile, c'était très bien. Très bien, c'était une belle présentation. On va essayer de retourner. Because international conference, we will just only switch the laptop. this is the closing session.